To a physicist, and you've studied black holes, why are they so important from a theoretical point of view?
Because they lead to a major puzzle. They lead to what I would call a conflict of principles. The biggest events in the history of theoretical physics, and maybe in physics itself, is when principles that you deeply believe clash. And when principles clash, that's where progress is made. I'll give you an example. Let me give you an example that I like very much, and as an example of a clash of principles. You know, the Greeks had two different theories of the world. One was the theory of the celestial, the planets, the stars, and according to them, the motion of the planets and the stars and everything were governed by perfectly beautiful, elegant laws. Everything moved on perfect circles. And then there was the terrestrial. And the terrestrial was ugly. Things fall on the floor, carts get pulled by horses, and if they don't continue to get pulled, they grind to a halt. It was corrupt. Two different theories of the world, and they didn't coexist. That persisted until Galileo. And Galileo put an end to that by one simple observation, a thought experiment. The thought experiment was, you take a rock, which is terrestrial, an ugly thing, and you throw it far into the air until it goes into orbit around the planet and it becomes celestial. The terrestrial rock became a celestial body. There must be one unified description of both. We're in kind of the same situation. We have two separate theories of nature which are incompatible, apparently, and which need to be put together. One of them is the theory of the very, very small, quantum mechanics. The quantum mechanics of atoms, molecules, and so forth, the uncertainty principle, all these marvelous things that were discovered at the beginning of the 20th century about microscopic physics. At the same time, physicists, Einstein, the same guy incidentally, was also thinking about the very big and the very heavy. He was thinking about gravity. Gravity governs the very big and the very heavy. Quantum mechanics governs the very small. Two different domains of parameters, two different regimes of the world, just like the Greeks had. Okay? Well, some people have the view that there's no need to put them together. There's no need to put them together. One governs the very big and the very heavy. Other, is very small. Why bother looking for a theory which combines them both? They're two different domains of the world. Then you have black holes. Black holes are Galileo's rock that he threw into the air, which belonged to both regimes. Black holes are objects which belong to both regimes. They're big and they're heavy, but they have quantum properties. In fact, they're very quantum mechanical objects. The fact that they belong to both domains tells us we have no choice. We have to put these two theories together. We have to make sense out of them, even though they appear to conflict with each other. We have no choice because black holes are the entry, and just like Galileo's rock, black holes are the entry into the world that combines them both. Okay. That, to me, is why they're so important.
Okay.